Okay, let's take a look. I want to just very briefly, section 1.6 talks about solving linear inequalities. Okay, so let's just very, very quickly review it. And the stuff I want to cover. What do you got?
I just need to look over your information on this, wherever it is, and then if it's correct, sign off.
Okay.
Oh, wait.
Okay, here's the stuff that I want to just review real briefly. You know, what is a linear inequality? How do we solve them, simple ones, and then how do we deal with harder ones, compound inequalities? Okay, so inequality is just, I mean, these ought to look familiar, right? Those are the inequality symbols that we work with. Less than, greater than. What does it mean if I include the little... Okay, good. Less than or equal to, greater than or equal to. This one's a little different. We don't use that one as much. What is it?
Not equal.
Not equal to, yeah. Okay. And not equal to, by the way, works exactly like an equal sign. All the algebra is identical. The only difference is it's not equal to. Now, for the other four, and you've used these a ton in the past, using them is almost the same as dealing with equations. Dealing with inequalities is virtually the same. There's just a couple very, very slight differences that we want to draw attention to here in a second. Okay, so what is a linear inequality? Well, linear means everything is to the first power. So we got no squares, no square roots, things like that. One variable we're dealing with, you know, typically it'll be x, but it doesn't have to be. Okay, so there's an example of a linear inequality. Now, a solution. Let's think about what a solution means. A solution of an equation, right, is just the value of x that makes the equation true, right?
Yes.
Make sense? So for example, if I had something like this, what if I had 2x plus 3 equals 11? Now, what would I do to solve for x?
Subtract 3.
Subtract 3 and then
Divide by 2.
divide by 2. Now, do that in your head. What do we get for an answer? Okay, we would just get, for this equation, we would just get 4, wouldn't we? And we check it by just plugging it back in to see if it works, and it does. Right, I get 2 times 4 is 8, plus 3 is 11. Check. So that's the solution because that's the only value of x in this case that makes the equation true, right? Now the same idea is true for inequalities. We want to find the value or values of x that satisfy the inequality, that make it true. Okay, but this is a little bit different here now. It's the same idea, but we only got one answer here. How many answers am I going to get for, say, this inequality? 7? Several. Okay, yeah. Several, maybe even more. Can you think of one? What's a value of x that would work here? That would make this inequality true? 1. Let's try 1. 1 seems to work, doesn't it? If I plug 1 into that, if I plug 1 in, I'm going to get 2 times 1 is 2 minus 3 is negative 1. Is negative 1 less than 8? Yeah. So x equals 1 is an example. What's another one? 2 would work also. 2 times 2 is 4, minus 3 is 1. So x equals 2 also works. Now, I could do this for a while. How many values are there total that would work?
Any number less than 5.
Okay, it's going to be any number less than, well, okay, any
5 or less.
5 or less. If we're talking about integers, right?
Yeah.
Okay, but we don't even have to restrict ourselves to integers. We'll find. How many are there going to be total? How many numbers? Integers, fractions, you name it. Infinite number, right? There are an infinite number of values I could take that would work. And so the solution, we can't just say the solution is something like x equals, what was the last one? X equals 4. It's not going to be quite like that. We're going to have to list all the x values that do work. But fortunately, they're going to be organized. There's going to be some boundary value that's going to be the threshold where numbers greater than that won't work, and numbers less than that will, or something like that, right? But our solution, I want you to keep in mind that when we provide the solution, when we solve this thing and get an answer, it's not just a single value anymore, it's an infinite number of values. Okay, so let's see what happens here. So lots of things it could equal. Now, real quick, the steps we go through to solve an inequality, adding and subtracting, same as before. We can treat both sides of the inequality equally by adding or subtracting the same number to both sides. Same with multiplying or dividing by positive numbers. But what's the difference here, the key difference? If I multiply or divide an inequality by a negative number, what do I have to remember to do? Flip the sign. Very good. Okay, so we've got to flip the inequality sign in that case. So let's take that one we started with. What are the steps I would go through to solve this? Okay, you can add 3 to both sides. Okay, and then
Divided by 2.
divide by 2. Okay, and so that gives us our answer. X is less than 11/2, so 5.5 if we make it a decimal, right? So there's an infinite number of values of X that would work there. Literally any number that is less than 5.5, whether it's an integer, a fraction, irrational number, it could be a square root, it could be anything. All those numbers work. So really the best way to, well, we'll get to it in a second. Let's solve this one. What do I do first? Then we'll look at the graphs in a second. Subtract 7, okay. Now what? Okay, red flag there. We got to flip the sign. We divided by a negative, so we got to flip the sign. Good. Okay, now if we look at the at the graphs of these, remember that we get open dots when we have less than or greater than inequalities, right? Because in those cases, we're actually not including the endpoint. It's just all the values that are either to the left or the right of that on the graph, less than or greater than, but not including. If we're actually including the endpoints also, so we've got a less than or equal to, or a greater than or equal to, then we have to have a closed dot because we're including the endpoint. Here's how you remember that. You probably already know this, but it takes more ink to draw a closed dot than an open dot. And so therefore, that's including that extra point. It includes the endpoint, okay? So if we look at the graphs of our solutions here, this is really the best way to represent the solution. In this case, what kind of an endpoint are we going to put? Open or closed? Open, and it's going to be a 5.5, and then we're going to shade in which direction? If we want all the x values that are less than that point. To the left, yeah, less than for left, okay? And so that represents the infinite number of values of x that would work. They're like the little dots on that line that create the line, right? Okay. What about this one? Our other solution was x is greater than or equal to -2. Solid or solid dot, shading to the right, because it's greater than, right? Okay, no big deal. Okay, what about if we have multiple values of x? Not a big deal. What do we do? Combine like terms. So what would that amount to here? Where do we want to put the x's this time? On the right. And this time it's a little bit more important, isn't it? We want to always collect the x's on the side where we have the most of them, because we would really like to have a positive number of x's, right? And especially with inequalities, because dividing by a negative forces us to flip the sign, and that's just one more possible mistake we could make. So let's subtract 7x from both sides. Now what?
Add 12.
Add 12. Okay, and divide by 3.
7.
Okay, and we get x is less, or now this says 7 is greater than or equal to x, but I want you to also realize that I can flip that whole thing around, right? We'd really prefer to have the variable on the left. That's okay. I can take this whole thing and flip it around, and what does it become? X is less than or equal to 7. So everything, including the inequality, gets twisted around with the inequality then, okay? Okay, and there's our graph. Good. Okay, compound inequalities. Compound just means more than one, right? So we can have two different varieties of compound inequalities. We can have and inequalities or inequalities. And inequalities technically are called conjunctive, and or inequalities are called disjunctive. So here's an example of an and inequality. They always look like this. The x is trapped in the middle, and it's got two boundaries. Now, how do I say this inequality correctly? Because people have a tendency, I'll tell you how not to do it. This is what most people want to do. They want to read it like a book and go left to right. Most people want to say -3 is less than x, and 1 is greater than or equal to x. That's really not the way to do it. We want to emphasize the fact that the x values included here are trapped between a lower value and an upper value. So does anybody want to take a stab at this? What's the correct way to say this? Dally Sue.
X is greater than -3 and less than or equal to 1.
Perfect. Let me say that again. X is greater than -3 and less than or equal to 1. That's a good way to do it, isn't it? Because it's telling us the x values are trapped between the lower value and the upper value. Okay? And if we look at, well, now how about the, well, ors are pretty obvious. Or inequalities literally include the word or, right? So this would just be x is less than or equal to -2, or x is greater than 4. Now when we look at the graphs of these two things, this is really important. When we graph an and inequality, a conjunctive inequality, the shaded portion is always going to be between those endpoints, isn't it? Because where we want the x values trapped between the lower value of -3 and the upper value of +1. And of course we're going to leave the left endpoint is going to be open because it doesn't include that endpoint. But the right endpoint, the upper endpoint, is going to be closed because we've got that equal sign there, right? And then we just shade everything in between. Okay? So and inequalities always look like that. They always are going to be an interval pinched between a lower limit and an upper limit every time. Okay? Does that make sense? Okay.
Yes.
Now an or inequality, and here's another thing I'll say about that. The word and fits. Because the shaded region has a floor and a ceiling. It has a bottom and a top, right?
Snap.
Okay, or inequalities are different. If I graph this or inequality, look, I've got two parts to it, two distinct parts that are different. I've got one boundary that's I've got an endpoint at -2 that's closed, and I'm graphing the x values to the left of that are less than. On the other side of this thing, I've got a boundary at 4 that's open, and I'm graphing all the values above it, right? The word or fits here, doesn't it? Because both of these two shaded regions don't have a bottom and a top. They have either a top value or a bottom value, but not both, right? This one is all the values that are less than or equal to -2, but there is no lower limit that caps it on the other side, right? The easy way to remember this is or statements always, think oars on a boat. So like the oars on a boat, they stick out to the side. When you row on a boat, the oars go out this way, right? So you're rowing, that makes sense? So think oars on a boat. Okay, solving these things, no big deal. It's the same kind of algebra that we were using before, only you're applying it to two inequalities, excuse me, at once instead of just one. So if I want to isolate the t, what do I have to do to get the t by itself here? Subtract 4. But I've got to subtract 4 from all three parts of that compound inequality, that and inequality, right? So I'm going to get a -13, a t in the middle, and a 6. And there's my answer. I'm done. Once I get the t by itself, I'm done. Okay, so when I graph it, this is an and, so it's going to be between those two values, -13 and 6. I get open endpoints and graph in between, right? Okay, last example. What about this one? Well, it's an or. Ors you just deal with one at a time. I'm just literally going to do both of these inequalities separately. So this one I'm going to add, I'm going to subtract 9 from both sides, right? Divide by -6, which means I have to
Flip the side.
flip the inequality. Good. And then on the other side, same kind of deal. I add 8 to both sides, divide by -3, which flips it. And so when I graph this, I should see like the oars on a boat. And I do. I get all the values that are less than -7, so off to the left, greater than 1, so off to the right. Okay. Now there's one additional example here that I want to give you that's that sometimes causes people trouble. It doesn't show up in this PowerPoint. One like this. What if I've got, okay, I've got -3, I've got okay, what do I do to solve for x? Okay, first I subtract 1. Good. Same order of operation stuff we were using before. So first step, I subtract 1. What's that going to give me?
4 less than or equal to -2x. Less than or equal to 11. Or 10.
10. Okay, now what?
Divide by -2.
Okay, divide by -2, meaning I flip the signs. So what's this going to give me then over here? If I divide everything by -2,
2.
I'm going to get 2, I'm going to get, and I'm going to get,
-5.
okay, and you already told me I've got to flip those signs around, right? Okay, that's my answer. That's kind of an awkward answer though, because when we have an and inequality, it's nice to have the x stuck in the middle, but have the bottom limit on the left and the top limit on the right. Does that make sense? This is backwards. So what's my resolution? What do I do to this thing? I take the whole thing and spin it around, right? I flip everything. So then what's that going to look like? So I'm going to end up with x in the middle. I've got my -5 there and my 2 there, but the signs get flipped with that, right? Does that make sense? Think of it as being on like a piece of glass. If I had this on a piece of glass and I flipped the glass around, the numbers would look goofy, but that's what it would look like, right? Okay, make sense? Yes.
How would you graph that?
How would I graph that? Okay, so then if I graph this, okay, I've got a lower endpoint at -5 that's going to be solid. I've got an upper endpoint at 2 that's going to be solid, and it's an and. That's it.
Dang. Ants are always.
Right.
The lines always.
Yep, if it's an and, the line, it's always going to connect the 2 endpoints. Yep, make sense? Okay, good. Good, have we got time? Let's see.
No, do we?
Yeah, we do.